Hey everybody, and welcome back to Software Engineering 1. So this week what we're going to be doing is talking about implementation. And this is probably going to be the most familiar sort of process in the software development lifecycle. You've already seen a lot of the technical aspects of this in a data structures class or in an algorithms class. And what we're going to do this week is we're going to really focus on the parts of implementation that are different between sort of at-scale software, production software, and programming assignments that you may have seen in other classes. And so if we go all the way back to the very beginning of the semester, we talked about some key differences between those programming assignments that you might be familiar with and sort of real-life production code. And what we're going to focus on here is the delta between those two in terms of what implementation actually means. So the module is split into 3 different videos. Each of them will hopefully be pretty quick so that you can focus on your group projects, but you can also kind of take away some things that you may or may not be aware of in terms of production level implementation. So up until this point, what we've done is we've really focused on all of the sort of front-end tasks for developing software. And so this spans requirements gathering, where you actually go out and you try to understand what the system is supposed to do, system analysis, where you put all of those pieces together into a sort of specifications document that you can use as a contract to agree with the client on what you're actually trying to do. And design, where you actually go and figure out what technologies you need and how to sort of technologically implement all of the different aspects of the system that you need to create. So last time what we did is we talked about how much work goes into the actual technical design of a system. And so the largest part of that is trying to decompose the overall system into smaller pieces that a whole bunch of people can work on in parallel, and that's a thing that we're going to talk about probably in the next video. But what we didn't necessarily talk about is how to put all of that, all of those sort of architectural ideas into practice. So we took a look at how you can answer architectural questions and what happens when you answer them incorrectly. And now what we're going to do is we're actually going to start talking about writing code and taking that architectural design and actually putting sort of rubber to the road, so to speak. So sort of the cornerstone of everything in terms of implementation is called software patterns. And so if you think about the difference between you yourself building a software or you yourself building a programming assignment and you and a team building a much larger piece of software, we've talked about how A, it involves a team, but B, it involves a lot of design decisions that you as maybe a junior developer won't necessarily have visibility into. So these decisions might be made in meetings that you're not in, or they might be made and you don't necessarily have enough information to even have an opinion on how something is going to be handled. So what will happen is typically people at the senior level or people at the architect level will come in and they will actually start implementing pieces of the subsystems. So they will actually provide examples of how things should be done. So if you think about really common activities, so CRUD activities, for example, creating a record and storing that record into the database, or reading records out of the database and then returning those to a UI. What might happen is the architect or a senior developer will give you some sort of concept of how that'll be done, or they'll give you a framework component that makes that very common sort of task very easy to do. And then what your job as a maybe junior developer would be is to take that pattern and then use that pattern to manage all of the different requirements that are in the subsystem that you're trying to actually implement. So if you go back to the conversation that we had about waterfall and how ultimately waterfall design really came from the ideas of construction and manufacturing and things like that, there's a fairly tight metaphor between building a house or building a building and building a piece of software. And if you think about that metaphor, these software patterns are effectively someone going in and sort of stubbing up the walls. You might have seen a framed structure where there isn't drywall and there isn't plumbing and there isn't a lot of the sort of things that make the building actually function. But you would definitely be able to see how big a room is, or how rooms are connected to one another through doorways, et cetera, et cetera. And so these software patterns effectively serve that same purpose. They tell you where a sink is going to go, they tell you where a window is going to go, and they tell you how all of these different subsystems might be put together. But they do not necessarily tell you how to put the drywall on, what color to paint the room, so on and so forth. And so what you hope is that in the system that you're trying to put together, there are really strong software patterns where you as a junior developer potentially aren't sort of left to your own devices with very little oversight. And then after a sprint is over, are told that you have to rework a whole bunch of stuff because it's not up to standards, or it doesn't use practices that the software company wants you to use. So in the very, very early stages of development, many things are sort of meant to be unclear. And so many of you in your group projects are in exactly this stage right now of implementation. You have an idea of what the system is supposed to do. You have some requirements, both functional and non-functional. You probably already understand what language the thing is going to be written in, and you kind of understand the libraries that you're intended to use. But you don't necessarily know how all these things fit together. You may or may not have a good idea of how everything is supposed to be structured. And so what ends up happening is this, exactly like many of the other processes, becomes iterative. You go into implementation, this fairly vague idea of what you're going to do, and then sprint over sprint, you kind of shore up all of those things. So it becomes less and less and less vague, and hopefully the code becomes better and better and better. So one of the things that I want to talk about here, and it's sort of heavily addressed in the textbook, and I think that you will find your experience in the group project will definitely reflect this, that you might have an idea that sounds great, and you want to maybe write it in Java, for example. And then some of the team members will say, great, Java it is. And so in your proposal or in your architectural design, you might specify that you're going to use Java, you're going to use these specific libraries, but then you might actually go away and try to implement the thing in Java, and you might realize that all of the libraries that you need are already available in Python, and Python's going to make your life better because everybody on the team already has Python experience. And so you kind of change everything at the end, at the 11th hour, and based on the type of architectural design that you have, that can either be really catastrophic or it can be no big deal at all. And so one of the things we didn't explicitly talk about last week, and I want to bring it up here, is you don't necessarily have to specify the language and the exact libraries that you're going to use top to bottom in an architectural design. What the architectural design is supposed to do is supposed to give you enough technical information that you could actually put the piece of software together. It's about decomposition, it's about maybe pseudo-coding things. It isn't necessarily about marrying yourself to specific technologies. What this is called is being language agnostic. So if you have a language agnostic design, what that means is you can get into the project, you can maybe get all the way to the second sprint, realize that you're spending way more time with language A than you would with language B, and then you can very easily change your mind about specific libraries or change your mind about specific languages, and all of the other pieces sort of just fall into place. Now, clearly, if you try to go from COBOL to Java, and so you're going from something that's very procedural to something that's object-oriented, you're going to have some issues, right? There's going to be impact to your architectural design. The point here is that if you decide to do something with C++, and you decide to exchange C++ for a different object-oriented language like Java or C#, or if you want to use library A and halfway through the project library A gets deprecated and you want to swap to library B, if your design is agnostic to those implementation details, you can do that very, very easily. And so we kind of tangentially talked about that last time. But what I want to make very concrete is that in the active implementation, sometimes you become aware of things that you would not have previously sort of dreamed up without actually getting your hands dirty in the code. So sometimes this programming language will be specified, and the libraries that you have to use will be specified. They'll either be implied by the architect themselves, or it will be tied directly to the needs of the client. But like I just said, these things can change over time. Software projects don't happen over a weekend. They happen over a very long period of time, and so as they go on, the needs of the client can change. The language the client is comfortable with could also change. So the case study that the textbook goes through is around COBOL. And so COBOL, you might be more familiar with it because of the sort of impact that it has on the economic stimulus payments caused by the coronavirus. But let's think about a situation where a client has a massive system like these states that have these massive financial systems that are written entirely in COBOL. They need the ability to run very large sweeps of checks. They need potentially to fix some minor bug that is very critical for them, but it is not like redesigning or reconstructing an entire system. So fundamentally, you always have a choice, right? You could always take this project and say, okay, well, you have COBOL, this thing is really old, you're gonna automatically have a bunch of technical or architectural debt tied to the project from the very beginning if you continue with COBOL. Why don't we just rewrite the entire system in C++ instead of COBOL, and in so doing, fix the bug? So instead of addressing the bug directly, what we're going to do is we're going to start this whole new software project. We're going to rewrite everything from COBOL to C++, and we're going to fix the bug while we're working. And so this is a thing that happens all the time, particularly in government or very large private companies might undergo things like this to try to get rid of architectural debt that they recognize is going to become a problem ultimately. However, it's very likely that just learning enough COBOL to fix the bug is way more cost effective. So if it's only one bug, like they can't see a specific field on a specific form, it's probably maybe a week of work to learn enough COBOL to figure out whatever proprietary system they're using for UI to show that value, or calculate a value correctly where it's previously incorrect. Fixing Y2K bugs, for example, it would be maybe a week to do that, maybe a couple of days to do that, but trying to rewrite the entire system, particularly in something object-oriented like C++, from something procedural like COBOL could take years, potentially. And so you don't necessarily want to agree to a year worth of work if you're a client, even if it would save you time in the long run by paying down architectural debt. So, you have to remember that technical debt and architectural debt themselves are really, really problematic. And ultimately, a system that is written in COBOL is going to have to be replaced at some point in time. Even though there's tons of COBOL in existence, there are going to be increasingly features that are supported by other languages that COBOL has no idea would ever be a thing, because COBOL was not written with those features in mind. So things like trying to send text message two-factor authentication codes, for example, is not a thing that would be super trivial to do in COBOL, I would imagine. So as you try to incorporate more and more and more of those features into your system, it's going to become more and more obvious that COBOL maybe is not the correct language for you, and the impact of that architectural debt goes up higher and higher and higher. So we talked a little bit about how the language impacts the client, but the language could also impact you as a software organization or a member of a software organization. So potentially, the client doesn't care what the programming language is, and often they won't unless they have other systems that are explicitly written in one of these languages. So what happens if you are a part of an organization and that organization has a collective 500 years of COBOL experience? You're somehow the most premier COBOL programming shop in the world, and all of your institutional knowledge is wrapped up in COBOL and all of these COBOL frameworks that you know how to use. If you try to usurp that institutional knowledge and you try to build a new application or fix an application in another language that you maybe only have a couple of years of collective experience in, you're obviously going to take longer to do it, and the quality of software that you produce is obviously not going to be as high as if you had used your language of choice. So it's probably best to use your language of choice even if it's really, really old. That said, if you are working at a company in 2020 that has 500 years of collective COBOL experience and only a couple of years of collective experience in other languages, that probably means that you're working for some sort of legacy support software company, and you accept the fact that you're very, very good at legacy support. If you are trying to build new applications in COBOL, this is kind of a crazy situation. So this really is meant to illustrate the fact that just because COBOL is old doesn't necessarily mean it's the wrong choice for a project. It could either be the right choice if you are very good at COBOL, or if the client is really married to COBOL with other applications that they have. So it seems like I've been talking about COBOL, and the book talks about COBOL as this sort of arbitrarily esoteric thing. And if you want, one of my favorite things to do is to go to TIOB online and look at the different programming languages and their relative impact, or how many lines of active code are running in each of these languages year over year. And so there was a report at around the end of 2016, something like that, that COBOL actually had the largest number of production lines of code running by, I think, nearly an order of magnitude. So at the very second of this recording, there are some quarter of a trillion lines of COBOL running worldwide. And these things are running not trivial things, right? They're running banks, they're running large financial lending institutions, they're running governments, they're running not necessarily taco stands and things like that. So you have to be aware that even if a language is very, very old, or frameworks are very, very old, concepts are very, very old, procedural analysis or classical design kind of old, you still have to be aware of it, because there is a very non-zero possibility, potentially a double-digit possibility, that you're going to see it at some point in your career, if for no other reason than because you're going to ultimately try to rewrite one of these systems in a more modern language. And so the example that the textbook ends their discussion with is a bank that tried to replace their COBOL code base with a C++ object-oriented system, and it cost them 5 years and almost $1 billion, so $750 million. That is a tremendous amount of money, even for a bank. And so in order to make a decision that large, you know that something has to highly motivate the bank. So you have to, as a software company, come in with a very good reason about why you want to replace their whole COBOL stack with something more modern. So we've talked about the design specification and how the design specification really serves as a contract between you and the client. And contractual obligations can very often lead you down these weird paths where you agree to do something like implement an object-oriented system in COBOL, which is not even a possibility. So what you want to be sure of is that if the client is trying to integrate their new system with legacy systems, that you can even support that you know how to do it, that there is some framework that allows you to communicate between those. And this is becoming less of an issue in the private sector. So talking about privately owned banks, talking about large corporations. But if you are looking in the government sector for work, and particularly in the Tallahassee area, there's a ton of work in the government sector. This is something to definitely be aware of. So if a client or a government institution or an agency is trying to build a new system, but they are reading data out of a very old legacy system, you have to be aware of the impact that that legacy system will have on your new system. And you have to be kind of aware and bake in all of the budget that you need to potentially reverse engineer some of the older stuff to be compatible with a new language or to be compatible with the new framework you're trying to introduce. So it is, at this point, a meme. I think that it's been in South Park several times. The idea of kind of scrolling really quickly through a terms of service and then clicking agree, it totally works if you're just getting the latest iTunes, which I think is dead now, or the latest Spotify or whatever. It does not necessarily work if you're trying to sign something like a master services agreement with a new client. So if you're trying to negotiate your specification document and you do not read through all of the crazy legacy code stuff that they put into that specification document, like you have to read magnetic tapes in order to get data pushed into your new system, then you can really do yourself and your organization a disservice because you could spend many hours trying to do a thing that could potentially not even be possible at the end of the day. So one of the things you have to be very cognizant about is the impact that other systems will have on the system that you're trying to actually implement today. So if you are trying to choose a language, this can happen either at the design phase, which is maybe less great because it's almost certain when you're choosing a language at the design phase that you're going to marry your design to that language. If you have already sort of built a language agnostic design and you are trying to choose a language to implement that design in, there are a couple of different things that you want to consider. And so the very first one, and I've actually talked to several teams about this week, you want to choose a language that the majority of your team is comfortable with. If you are in a group project in a semester-long class, or if you're in a new sort of project for a company, you do not want to try to learn a bunch of language features at the same time you're trying to use those language features to build a new application. It seems like a great idea because it seems like you're going to get something out of the experience and you're going to be able to fulfill your obligations. It usually ends up being not super great. So what you want to try to do is stick with languages, stick with libraries that you are well versed in, and that you and all of the team members actually understand and know. You also want to be cognizant of the non-functional requirements. So this is particularly true in terms of performance and in terms of security. So if you want an extremely blazing fast application and you try to implement that application in C# or in Java, you have, again, kind of missed the mark because both of those languages are going to require a virtual machine, and that virtualization is going to automatically make it slower than something like C or C++. If you're trying to build a really performant application and you choose a language like Python, it's going to be very hard for you to have the highest performance simply because the language is not compiled. So you're going to have some optimizations that potentially you can do to meet the non-functional requirements, but it's going to make the bar a little bit higher for you to clear. And you also want to think about the limitations of your architecture. So if you're trying to build an object-oriented system, you've done object-oriented analysis, and you've presented an object-oriented architecture or design for the project, and then you choose to do the project in COBOL, or you choose to do the project in C because of something like performance, that is going to have a severe negative impact on your ability to perform correctly. What's going to end up happening is your architecture or your design document is going to get thrown out the window. You're going to have to do a substantial amount of rework on that document, or you're going to have a huge deviation between what you actually implement and what you said you were going to implement in the design document. So object orientation is maybe the quintessential example of this. And so we talk about object orientation a lot because we teach object orientation a lot in terms of curriculum. The same thing goes for functional programming. The same thing goes for name your favorite new type of programming. What we've done is we've talked about object orientation from the perspective of design and analysis, but implementation is where you can actually start performing object-oriented programming. And so as we said, in both the analysis and the design videos, what you don't want to do is you don't want to have your analysis or your design document go to such granular detail that you're actually implementing classes in those documents. And so there will very likely be helper classes, there will be minor classes that you have in the actual implementation that have documentation but are not necessarily in the architectural design itself. And that's entirely okay. Because implementation is where you're actually implementing the code, you're actually getting into the sort of nuts and bolts of the technical details. So if you have used object-oriented analysis and you've used object-oriented design and you try to implement in C, you are fundamentally missing the mark and you're going to have a really hard time trying to actually do your job correctly. So this is another example that we see where if you make a decision here that's contradictory to a decision that you made previously, you have to go back to these other phases and then fix that sort of contradicting decision that you made, and then potentially rework a whole bunch of stuff from that previous phase all the way up to the phase that you're currently in. And so this can happen not just because you were not paying attention, but it could happen because something like a person leaves the team. So there are small software companies all over the country, all over the world, that buy into a project because one person is really, really good at pick your favorite technology. They're very, very good at Android development. They're very, very good at Kotlin. They're very good at whatever. And that person leaves the team either by force or by decision or by whatever. And now the rest of the team, the knowledge gap between that one person that was integral to the project, everyone else is very high. So now you have to pivot, and you potentially have to pivot to the point that you're making a contradictory decision to go back to something like Fortran, where the original developer had all these ideas for Java. So this is kind of a cooked up example, but you can see how this would happen particularly with libraries. If you have libraries that are sort of esoteric, that are kind of bleeding edge, and the only person that knows how to use that library is now gone from the team, it could take very long time for somebody to kind of reverse engineer exactly what's supposed to be happening with that library. And so instead of doing that, they might sorry about that. They might want to just write it in a different language entirely or use a different library. And in doing so, you can make some contradictory decisions and have to go back and do some rework. So programming languages themselves, if you're thinking about trying to decide which programming language is right for your project, are typically talked about in a variety of different ways. So you can talk about them in terms of how they type variables. You can talk about them in terms of if they have virtualized environments or not. One of the ways that you might not have seen before is called the sort of language generations. And so here is a list of all of the generations that are provided in the book. And so basically what you see is that the earlier the generation of the language, the closer to like assembly or actual binary it is. So first generation, you have actual sort of binary files that run directly on a processor. At second generation, you get instructions, set architectures, and assembly languages that sort of abstract up from that binary language. By third generation, you get things like Java and C# and Fortran. And then if you think about fourth generation languages are really kind of specialized languages typically, or they are what are called scripting languages. So common examples are things like Python or things like Perl. You could also have things that are very, very niche, like Maple. Maple is really closer to MATLAB than a truly sort of Turing complete language. And you also have query languages like SQL. So there are a lot of studies about which of these is best for what kind of software project. But what we want to focus on in this last part of the video is these 4th generation languages, because they give you a lot of features that these other languages don't necessarily give you. So 4th generation languages are kind of a league of their own because of the level of abstraction they give you as a programmer. So compared to a 1st generation language where a single binary instruction is literally one binary instruction, you could have something in Python that like an enumerated list, for example, or list coherence or something like that, that generates a crazy amount of instructions or binary instructions for that one actual keyword in the language. So for every line of code that you're writing in Python, you're actually writing a very large amount, or a much larger amount, of code that's actually running on the processor. And so if you think about the number of lines of code that you have to write in C to do something like simulate the command line or terminal, and then you compare that to the number of lines of code of Python you have to write to build an AI neural network to beat a video game as complicated as Dota. It is much less code to build this neural network than it is to even do some simple simulation. And so that is basically what I mean by allowing you to do more with less lines of code. And the entire point of most of these languages is that they simplify the entire development experience. And what they do is they allow you to do technical things without necessarily understanding the underlying engines that are actually doing the technical work. So most of the time, these languages themselves are non-procedural, and you can think about SQL as being the perfect example of this. It's really a set-based language for querying. It isn't necessarily a language where you would want to sequentially or procedurally do something. And most of the time, if you try to write a procedural program in one of these languages, you don't get the results that you expect. And so the perfect example of this is trying to do something with a cursor in SQL. So if you've ever taken a databases class and you know what a cursor is, it's basically a glorified looping structure where you can iterate through the rows of a record set that's returned to you by a query. And so there's a company that I interviewed with in town one time, and the guy that did the technical interview actually referred this, and this should actually probably be in quotes. They referred to cursors in SQL as the devil dressed like syntax. And so people have these very deeply seated feelings against things like cursors simply because their performance is quite bad. And if you're trying to do something with a cursor, often there's a way better way of doing it that consumes fewer resources and gets the job done faster. So with one of these non-procedural languages, what you're trying to do is you're trying to tell the computer what to do and not how to do it. And so as a programmer, what you're trying to do is you're trying to bake in a lot of optimization in your code. And so over the years, it's become kind of an almost stereotype that computer science majors, programmers in general, want to do a job with as few lines of code as possible. That's certainly one type of optimization, but obviously there's going to be optimizations where you try to make your algorithm the fastest or your algorithm take the least amount of space possible. And so what you're doing with these non-procedural languages is you are letting the interpreter do most of the optimization, and you are kind of hands-off, your arm's length as the programmer. This is not the favorite situation of most programmers, and so these are kind of issues that you run into with fourth generation languages. So the reason I bring this up is that one of the most popular things, especially for enterprise level software, which we're going to talk about in the software organizations module in a couple of weeks, is customization frameworks. So you see very large companies like Salesforce.com, you see very large companies like SAP doing a tremendous amount of work building frameworks that then companies come in and they actually try to buy the framework pieces and then put them together into their own system like Legos, essentially. if you build a customization framework into your application and you use something like C++ or you use something like Java or you use something like C#, what you're doing is you're requiring the client that bought the system to have an in-house developer that will help them customize the piece of software. But if they had an in-house developer, it's very likely that you wouldn't have been building the software to begin with. Their in-house developers would have been building the software. And so, fourth generation languages are fantastic for actually implementing these customization frameworks. And the reason is because the user doesn't have to compile anything. They don't actually have to have the same compiler. They don't have to understand the optimization flags. They don't have to side load binaries. They don't have to do anything complicated like that. All they have to do is write some code in an extremely high level language that they're going to have a better time understanding. They get to focus on things that they are familiar with, like their own business data, and then you can hot swap those scripts because something like Python is not compiled. So it's interpreted, and you can pick up the latest and greatest script, and you can send that off to the interpreter that's baked into your piece of software without a whole bunch of fuss. And so customization frameworks are the number one place where languages like Python really kind of shine. You're able to pass customization work off to business analysts or off to data scientists that are very, very good at Python, but don't necessarily have to know all of the sort of best practices and all of the scalable software concepts that you as a full developer do. So on the flip side of that, where do fourth generation languages struggle? So the very first one is performance. So like we said before, SQL can be extremely fast. Python can be extremely fast. If you try to write an algorithm in Python and you try to write an algorithm in C, almost 100% of the time, the C algorithm will be faster than Python. It's just kind of the way that the world works. The speed of light, in some ways, hinders Python's ability to be as performant as something like C. It is the case that interpreted languages themselves are almost always universally slower because interpretation optimizations are harder to perform than compiler optimizations. And compiler optimizations persist because they're baked into the binaries themselves. So interpreted languages just kind of have some performance issues that compiled languages do not necessarily have. So the next point is that it's very good to have customization frameworks built in fourth generation languages because it allows users to do really crazy things. But on the flip side of that, it allows users to do really, really crazy things. So potentially a user could do some horrific thing like drop a whole database table in a Python script and not actually realize what they're doing. So potentially by opening up a customization framework with a fourth generation language that somebody can easily access like Python, you could give them the keys to the kingdom without really wanting to do that. And so when you implement these customization frameworks, it's a really good idea to make sure that you aren't sort of giving carte blanche access to data that you otherwise wouldn't want people to have access to. I actually had at one point, I saw a person destroy a virtual SQL server with a whole bunch of cross joins at one point in my life. I have actually seen people accidentally drop the database trying to do selects from the database. These kind of things are very, very easy to do, and the easier you make them to do with your customization framework, the worse your life is going to be, because essentially what's going to happen is your application is going to be on the hook for giving somebody access to drop a database table or delete a whole bunch of production data. So what you want is you want to give business analysts and data scientists as much access as physically possible while also mitigating their risk of accidentally doing something untoward that they are not prepared to fix or that they may not even understand they have access to. So if you think about the way some customization frameworks work, it's basically just a white box and you're typing into the white box, and even if you're the best data scientist in the world, you may not have any understanding of the context that your code is running in. So you, as the person using the customization framework, don't really have enough context to understand how to mitigate your own risk. So the person who's implementing that piece of the system really has to do it for you. And so that's a really important point to remember. So the last thing we're going to talk about is coding practices. And so once you have selected the language that you want, once you have thought through all the libraries that are associated with that language, what you need to do is you need to think about all the kind of basic parameters, kind of rules for the playground everybody's going to abide by when they're trying to perform implementation tasks. So there are two primary pieces of documentation that companies use to kind of enforce these rules. The first is a style guide. So style guides are basically a way to enforce that everybody's code looks the same. And the idea behind this is that if everybody's code looks the same, then everybody will be able to read everyone else's code and kind of immediately understand it. There won't be a whole bunch of cognitive dissonance between your code and then the 5 or 6 other people's code on the team. You also have code guides. So code guides are actually there to enforce those software patterns that we talked about at the very beginning. So the idea is they're trying to make everybody's code adhere to the most basic principles and keep it as simple as possible, so that one person's not using one way of accessing the database while another person's using a different way and another person's using a different way, and all of those could potentially have different bugs with them. So we've talked a lot about programming languages in this lecture, and there's this kind of weird concept called the language wars. And it is widely studied in the software engineering research community, and you have probably had these conversations with your friends before. The idea is that there is always going to be a person that thinks that their language is best at everything, but it's true that most languages have a time and a place where they are the appropriate decision to make. And so people can really have these almost religious fights about architectural design decisions, and they can also have them with what languages to use and the relative merits of whatever language or whatever library or whatever design decision that you make. So it's really, really important to think about the impact of coding practices and the impact that they have on your team's ability to do their job. So the best concrete example of what I'm talking about comes from group projects of old, right? So there are people that refer to themselves as Pythonistas who have the most idiomatic Python skills in the whole world. And to a person with very good Python skills, this is the most expressive code. It's very small, typically it's very compressed, it's very terse. And the problem is if you have a person that is on your team, even one person that does not understand very Pythonic Python, they are going to have a very hard time trying to contribute code and trying to fix bugs in code that is messed up. So even though there is a concept of how Pythonic your Python is, and there is actually a metric or a scale that you can use to figure out where on that scale your code lies, it is kind of an academic exercise to do that. What you want is coding practices and coding guidelines that actually let you do work and do high quality work. So if you have somebody that is new to Python, you don't want to force everybody to use hyper idiomatic Python just because it's cool, just because you feel like it's the right thing to do. So if you have components of idiomatic Python that you have a reason for, certainly you can teach that new person, but you don't necessarily want to saddle them with unnecessary burden that's ultimately just going to be technical debt for everybody to pay down throughout the life of the project. So to put all of that, sort of put a pin in it, there is a saying that if your code works and the code has infinite amount of technical debt and it just is put together with duct tape and it works, that's a way better situation than having the best sort of academically perfect code that fundamentally doesn't do the thing that it's supposed to do. And so what you're going to find is by maybe Thursday of next week, the first iteration of the project is due on Friday. You're going to find that maybe midnight on Thursday, you're going to be very aware of sort of the corners that you could potentially cut and get a working prototype into the first iteration, or some functioning features into the first iteration that you could actually show off in your video. And you're going to make those concessions, and that's entirely fine. That's a thing that happens in industry all the time. The point of the class at the very base of it is that you're trying to make the smartest concessions physically possible and cut the corners that you know can be cut, and impact the project negatively as little as possible. So if you find yourself making concessions, welcome to the real world. That's totally fine. Just make sure that you're doing so mindfully, and that you are not amassing such a ridiculous amount of technical debt that you're going to have problems with iteration 2 or iteration 3 trying to dig out from underneath it. Code authorship is sort of where all of this kind of ends. We talked about this in the very first video, how one of the most basic differences between a programming assignment and scalable sort of production software is that you are not the only person that is trying to do the job. And so if you have written a bunch of code that is very, very idiomatic, but is not readable to a sort of normal person, that is probably going to have a much larger negative impact than whatever positive impact you got by using idiomatic approach. Likewise, something as simple as using really bad variable names can lead directly to a project failing, just flat out failing. And so there are accounts that I've heard of people that have done crazy things like naming the internal or the private variables inside of a class after their ex-girlfriends or their ex-boyfriends or something like that. And so if you get even a stack trace or an exception from that piece of framework code back to you, you're going to have no idea what any of the stuff means, because the variables themselves don't actually express what the variable is supposed to be doing. This seems like a really simple thing, and in a programming assignment you could certainly have variable names X, Y, Z, whatever, but when you do that in this sort of production code, what you're doing is you're setting the whole team up to potentially fail, which is not a great situation to be in. So what we're going to do next time is we're going to springboard off of that idea and sort of talk about what are called lexicon bad smells, which is sort of a hilarious name for these variable names that don't actually do anything other than make your life confusing and potentially make people make bad decisions. So thanks for tuning into this one, and I will see you next time.